Hello, my chemistry friends. So we are now in Module 12, and my next few videos are going to be over some of the extra practice problems that you can find in the back of your Apologia chemistry textbook, if you have the second edition, that is. If you do, I am on page 580, and I'm going to start with number 4. So number 4 says a mixture of nitrogen and oxygen gas are stored at a temperature of 25 degrees Celsius and a pressure of 1.0 atmosphere. If the partial pressure of nitrogen in the mixture is 0.7 atmospheres, what is the partial pressure of oxygen in the mixture? Now, as you can see, I have actually used my blackboard this time, and I wrote down all of the equations from this module. So the way that I like to get started, excuse me while I pick over some of my daughter's toys that are at my feet. I'm glad you cannot see the state of my house right now. All right, number 4, I'm going to put right here what we are looking for. So we're looking for the partial pressure of, what was it? Oxygen. So that'd be O2. And then we write down what we know. We know the temperature is 25 degrees Celsius, which is equal to 298 Kelvin. And we know that the total pressure of the nitrogen and oxygen gas is 1.0 atmospheres. So we're going to write P total equals 1.0 atmospheres. And we know that the partial pressure of nitrogen, N2, is 0.7 atmospheres. All right, so looking at the information that we have and what we want to find out, which equation over here would we use? Well, I believe they told us the temperature just so that we would know that this is at standard temperature and pressure, so it's an ideal gas. So we can use any of these equations, but temperature doesn't need to be part of the equation because all we're really needing is this equation right here. The pressure for the total gas mixture is equal to the partial pressures of each of the individual gases. So that would mean that in this case, P total would equal the partial pressure of nitrogen plus the partial pressure of oxygen. So we want to solve for oxygen, so we're going to subtract both sides by N2 minus P of N2. So these on this side cancel out, so we just solved for the partial pressure of oxygen, which should be equal to the P total, the total pressure of the gas, minus the partial pressure of nitrogen, N2. Did you ever think you would have a simple subtraction problem in this class? Well, here it is. So now we just have to do 1.0 ATMs minus 0.7 ATMs. Oh my Lanta, we don't even have to use a calculator for this one. So the partial pressure of O2 equals 0.3 atmospheres. Ta-da! And I think they gave us a short one for number 4 because number 5 is very, very long. So let's move on to that one. Erase this. We're going to need all of our space. It is a glorious day here in Michigan today. The sun is shining in, lighting up my schoolroom here. It puts me in a good mood. All right, number 5 says, a mixture of gases has a pressure of 1.5 atmospheres. The mixture is analyzed and found to contain 0.200 grams of H2, 4.00 grams of CO2, and 1.45 grams of N2. What is the partial pressure of each gas in this mixture? All right, let's set this up again. So what are we looking for? We are looking for the partial pressure of each gas in the mixture. So we've got H2, P of H2, we are looking for P of CO2, and P of N2. We have to find all those partial pressures. What do we know? We are told that the mixture of gases has a pressure of 1.5 atmospheres. That means that the total pressure of all those gases together, so P with the T down here for total, equals 1.5 atmospheres. And then we are told how many grams of each of those gases there are. Well, if we know grams, then we can always figure out moles, right? So let's write those down. We know we have 0.200 grams of H2, which means, well, it's not equal to, which means we can figure out the moles of H2. And then we have 4.00 grams of CO2, so we can figure out moles of CO2. And we have 1.45 grams of N2, so we can figure out moles of N2. All right, so looking at the information that we have and what we are looking for, we have the different number of moles for each of the different gases. We have the total pressure, and we need to figure out the partial pressures. So looking at my choices over here, okay, I can tell that I'm going to need to use this equation. The partial pressure for each component, this says, in case it's too small, the partial pressure for each individual gas is equal to its mole fraction, that capital X, times the total pressure for the mixture of gases. So let's get started by figuring out how many moles of each of the gases we have. 0.200 grams of H2 multiplied by 1 mole of H2 over the mass of H2 would be 2.02 grams of H2. Hey, quiet in the kitchen. Excuse me there. So we've got 0.0990 moles of H2. Next, 4.00 grams of CO2. We're going to multiply it by 1 mole of CO2 divided by the mass of 1 mole of CO2, which would be 44.0 grams of CO2. Remember, I'm finding that information from the periodic table, the beloved periodic table. That would give us 0.0909 moles of CO2. And then we have 1.45 grams of nitrogen. Multiply it by 1 mole of nitrogen divided by the molar mass of 2 nitrogens, which would be 28.0 grams. So that gives us 0.0518 moles of nitrogen gas. Okay, that's how many moles I have for each of the separate components. Now, in order to find capital X, the mole fraction, I also need to know the total number of moles in the gas mixture. So I'm going to add these all together. I get 0.2417 total moles. Now I can find the mole fraction for each one. I told you that this was going to be a long problem. Okay, so the X for H2 would equal the moles of H2, which is 0.0990, divided by the total moles of the gas mixture, which is 0.2417. So the mole fraction is 0.410. Okay? Mole fraction for, next is CO2, equals the moles of CO2, 0.0909 divided by the total number of moles in the mixture, which is 0.2417, equals a mole fraction of 0.376. And then the mole fraction for N2, which would be equal to 0.0518 divided by 0.2417, gives us a mole fraction of 0.214 for nitrogen. Now finally, the last step. In order to find the partial pressure for each component, we are going to multiply its mole fraction times the total pressure of the gas. So for hydrogen, I'll draw a little curvy line here. The partial pressure for hydrogen would be its mole fraction, 0.410, times the total pressure. Remember, we were told that in the problem, which is 1.5 atmospheres. So the partial pressure of hydrogen would be 0.62 atmospheres. There's one answer. Okay, the partial pressure of carbon dioxide would be its mole fraction, 0.376, times the total pressure of the gas mixture, which is 1.5 atmospheres, giving us a partial pressure for carbon dioxide of 0.56 atmospheres. And lastly, getting to the very last calculation, the partial pressure for nitrogen would be its mole fraction, 0.214, times the total pressure of the gas, 1.5 atmospheres, equals 0.32 atmospheres. And I finished just as my husband went outside. Isn't he noisy? I think that you could hear a bunch of background noise and rustling in the kitchen. He's noisy, and he just came home, and my welcome to him was quiet in the kitchen. Oh well, I will greet him more warmly now. I hope that you understood numbers 4 and 5. My next video will continue on with these practice problems.